For almost 70 years, every computer chip on Earth, no matter who made it, has been built on the same basic idea. Take a thin, flat piece of material called a substrate and use it as the foundation that holds all the tiny silicon components together, wires them up, and lets them talk to the outside world. For most of that history, the substrate itself was the boring part of the story. Nobody wrote headlines about it. All the excitement went to the silicon, the transistors, the nanometers. The substrate was just the plate the meal sat on. That quietly changed in 2026 when China declared this the first year of large-scale glass substrate production. And companies across its display and semiconductor industries started shipping a material almost nobody outside the industry had ever thought to get excited about: ordinary-sounding, extraordinarily engineered glass. This is the real story behind the insane glass chip headlines circulating online, and once you understand what's actually happening, you'll see why serious engineers at Intel, Samsung, TSMC, and AMD are all racing toward the exact same material, and why China's aggressive, coordinated push into it has genuinely rattled the global chip industry's sense of who controls the next decade of computing hardware. Let's start with the problem this glass is actually solving, because it's not really about making a faster transistor. It's about something far less glamorous, but arguably just as important: the material that chips sit on top of. For decades, that material has been an organic resin substrate, essentially a specially engineered plastic-like compound, reinforced with layers of glass fiber cloth, built to be a stable insulating base that supports the silicon chip, carries power to it, and routes the millions of tiny electrical connections in and out. Organic substrates have been the quiet, reliable workhorse of the entire semiconductor industry since long before AI chip was a phrase anyone used. But they have a fundamental weakness, one that didn't matter much until chips started getting monstrously bigger, hotter, and more power-hungry, which is exactly what's happened over the last few years as the AI boom has pushed processor designers to cram more computing power and more heat into single packages than the industry has ever dealt with before. The core weakness is something engineers call warpage. Organic substrate material expands and contracts with heat at a different rate than the silicon chip sitting on top of it, and at a different rate again than the metal connections running through it. When you heat these mismatched materials up during manufacturing, and again every time the chip runs hot under a heavy computing load, they expand unevenly, causing the whole package to bow and warp, ever so slightly, like a thin sheet of plywood left out in the sun. For older, smaller chips, this warping was manageable, a minor engineering headache rather than a fundamental limit. But today's most advanced AI accelerators, the chips powering large language models and massive data centers, are being described by industry insiders as kilowatt-level processors, chips that draw and dissipate more electrical power than an entire hairdryer, concentrated into a package smaller than a drink coaster. At that level of heat and power density, warpage stops being a minor nuisance and starts becoming a hard physical ceiling, limiting how large, how densely wired, and how powerful a single chip package can practically be built, no matter how advanced the silicon inside it is. This is where glass enters the picture, and it's a genuinely elegant piece of materials engineering. The right formulation of glass can be engineered to expand and contract at almost exactly the same rate as silicon when heated, a property called a closely matched coefficient of thermal expansion. That single property largely solves the warpage problem at its root, rather than requiring engineers to design increasingly elaborate mechanical workarounds to compensate for it. Beyond thermal matching, glass substrates offer a handful of other properties that matter enormously for next-generation chips. They're dramatically flatter and more dimensionally stable than organic substrates, which matters because flatness translates directly into how densely you can pack electrical wiring. They have lower dielectric loss at high frequencies, meaning electrical signals traveling through them lose less strength and clarity, an increasingly critical property as chips are pushed to communicate with each other and with memory at ever faster speeds. And they support a manufacturing technique called through glass vias, or TGV, essentially microscopic holes drilled directly through the glass to create ultra-precise vertical electrical connections, packed at a density organic substrates simply cannot match. Put those properties together and you get a substrate material capable of supporting significantly larger chip packages, running cooler and more reliably under heavy AI workloads, wired with a density that keeps pace with the industry's relentless demand for more interconnects between more chiplets, memory stacks, and optical components. That's not a small cosmetic upgrade. Industry analysts increasingly describe glass substrates as the material the entire advanced chip packaging world has been quietly waiting for, precisely because organic substrates are running into a wall that better transistors alone cannot fix. You could design the most brilliant silicon chip in the world, but if the material underneath it warps, overheats, or can't route enough connections, the chip on top of it can never reach its full potential. Now here's where China enters the story, and it's a genuinely interesting case of an industry pivoting on an unexpected strength. China did not build its glass substrate advantage by starting from scratch in semiconductor manufacturing. It built it by leveraging an entirely different industry it already dominated: display glass. Companies like BOE Technology Group, the world's largest maker of LCD display panels, and other Chinese display manufacturers had already spent decades mastering the production of large, ultra-thin, precisely engineered glass sheets for televisions, monitors, and smartphone screens. That expertise in melting, forming, cutting, and precisely controlling the properties of specialty glass at enormous industrial scale turns out to translate remarkably well into the requirements of semiconductor-grade glass substrates. It's a bit like a company that spent decades perfecting the art of brewing beer at massive scale, discovering that many of the same fermentation and quality control skills apply directly to industrial biotechnology. The underlying expertise wasn't wasted. It was one pivot away from an entirely new, higher value market. By early 2026, this pivot had accelerated dramatically. BOE moved from small pilot production lines to full-scale panel production for semiconductor glass substrates. Chinese assembly and testing companies, including JCET Group, the country's largest outsourced chip packaging and testing provider, announced they had successfully integrated glass core substrates into cutting-edge products, including high-speed optical modules and a packaging approach called co-packaged optics, a technology that places optical, light-based data connections directly alongside a chip, rather than routing everything through slower traditional electrical wiring. That specific move put JCET in direct competition with Taiwan's semiconductor manufacturing company, the dominant force in advanced chip packaging worldwide, on a technology, glass-based co-packaged optics, that many in the industry consider central to the next generation of data center hardware. Meanwhile, smaller, specialized Chinese materials companies moved just as aggressively. One notable example, WG Tech, reportedly achieved a through-glass via manufacturing process capable of drilling holes with an aspect ratio of 100:1, meaning holes 100 times deeper than they are wide, at diameters as small as 5 micrometers. A manufacturing precision that puts Chinese suppliers within striking distance of the process capabilities long dominated by South Korean firms like Samsung Electromechanics and SKC's Absolic subsidiary. It's worth pausing on why this specific technical capability, through glass vias with extreme aspect ratios, matters so much, because it's really the crux of the entire competitive race. Drilling a hole through glass sounds simple until you remember that these holes need to be microscopic, extraordinarily precise, perfectly vertical, and free of cracks or defects that could compromise the glass's structural integrity or create electrical leakage paths. Glass, unlike the more forgiving organic materials it's replacing, is fundamentally a brittle substance, prone to cracking under the kind of mechanical and thermal stress that chip manufacturing routinely involves. Mastering how to drill millions of these microscopic vertical channels through glass without introducing hairline fractures that could cause a multi-thousand-dollar chip package to fail months later in a data center is an extraordinarily difficult manufacturing problem, one that separates laboratory demonstrations from products you can actually ship at scale with the reliability a semiconductor customer demands. The fact that multiple Chinese companies are now closing in on aspect ratios and precision levels that took South Korean and Japanese firms years to perfect is a genuine signal of how quickly this particular technological gap is narrowing. This is also precisely why Western chip makers haven't been sitting still, and it's important context for understanding just how significant China's move actually is. Intel has been pursuing its own glass substrate roadmap for years, and in January of 2026, it announced it had already shipped the world's first server processor, a Xeon 6 chip, featuring a glass core substrate in a genuinely commercial product, not just a lab prototype, an important proof that glass substrates could clear the incredibly demanding reliability bar required for products sold to enterprise data center customers. TSMC has developed its own glass-based packaging platform, aiming for mass production by around 2028. South Korea's SKC, through its Absolic subsidiary, has been racing to become the first company in the world to achieve full commercial mass production of glass substrates, a title with real strategic value in an industry where being first to market with a qualified, reliable product often locks in years of exclusive supply agreements with major chip designers. So China isn't creating this technology out of thin air or leapfrogging an industry that wasn't paying attention. It's racing into a technology that the entire global chip industry already recognizes as the next major shift in advanced packaging. And it's doing so with a genuine structural advantage, a domestic display glass manufacturing base that is, by scale, the largest in the world, now being redirected toward a new and far more lucrative purpose: It's that China may be positioned to become the first country capable of mass producing this increasingly critical material at the volume and potentially the cost that the rest of the global chip industry will need right at the moment when the entire industry is scrambling to adopt it. There's a broader strategic backdrop here too, one that connects this glass substrate push to China's wider approach to semiconductor self-sufficiency. Advanced chip manufacturing has, for years, been constrained by China's restricted access to the most cutting-edge lithography equipment, the machines used to etch the tiniest, most advanced transistor patterns onto silicon, largely controlled by a small handful of companies in the Netherlands, Japan, and the United States, and subject to export restrictions aimed specifically at limiting China's access to leading-edge chip manufacturing capability. Facing that ceiling on raw transistor miniaturization, Chinese industry strategists have increasingly focused on a different lever entirely: advanced packaging, the art of taking multiple, individually less advanced chips, sometimes called chiplets, and stacking, connecting, and packaging them together so cleverly that the combined system performs competitively with a single, more advanced monolithic chip that China currently cannot easily manufacture on its own. Glass substrates are a foundational technology for exactly this strategy, since they're specifically what enables denser, more reliable connections between multiple stacked or side-by-side chiplets. In other words, this isn't just a material science story. It's a piece of a much larger, deliberate industrial strategy to route around a manufacturing bottleneck by getting extremely good at something adjacent to it, something that happens to matter just as much for building powerful AI hardware. It's also worth being clear-eyed, in the spirit of separating real substance from viral exaggeration, about what this breakthrough does not mean. Glass substrates are not going to instantly replace silicon as the material chips themselves are made from. The headline "Made Silicon Obsolete" framing you'll see in some of the more breathless online coverage is a significant overstatement. Silicon remains, by an enormous margin, the material actual transistors and circuits are built on. Glass substrates replace the packaging material underneath and around the silicon, the supporting foundation, not the computing chip itself. It's the difference between redesigning the foundation and framing of a house versus redesigning the people living inside it. A better foundation absolutely matters. It can let you build a taller, more stable, more efficient house than you could before, but it doesn't replace what the house is fundamentally for. It's also worth noting that this remains, industry-wide, an early and still maturing technology, not a finished, fully deployed revolution. Most companies across the industry, Chinese and Western alike, are still in the qualification phase, the painstaking process of proving that glass substrates can survive years of real-world use in real data centers, under real thermal cycling, at the extremely demanding reliability standards that chip customers require before they'll bet billion-dollar product lines on a new material. Production volumes are still climbing from pilot scale toward true mass-market scale. Market analysts project the glass substrate industry growing rapidly, from an estimated market size in the tens of billions of dollars in 2026 toward considerably larger figures by the end of the decade. But that growth curve, however steep, is still a multi-year unfolding story, not something that flips a switch overnight. China's rapid progress in this space is genuinely impressive and strategically significant, but the country is still, by most independent industry assessments, closing a gap with South Korean and Japanese leaders in areas like through glass via precision, rather than having already definitively overtaken them. So why has this particular story generated the kind of shook the tech world headlines you're seeing? Because it touches a nerve that runs through the entire modern technology industry. The uncomfortable realization that the next major bottleneck in AI hardware might not be the thing everyone's been watching closely, the cutting-edge transistor, but something almost mundane by comparison, the humble material a chip sits on. For years, the public conversation about the U.S. China chip competition centered almost entirely on export controls over advanced lithography machines and the most sophisticated transistor manufacturing processes. That framing made China's path forward look narrow and difficult, boxed in by equipment it couldn't buy. The glass substrate story complicates that picture considerably, revealing a parallel front in the competition, one built not on the most exotic, tightly export-controlled manufacturing tools, but on industrial scale. Materials, science expertise, and manufacturing discipline that China had already quietly built up in an entirely different industry, display panels, and is now redirecting with remarkable speed toward the exact bottleneck the global AI hardware industry is racing to solve. That's the real insane part of this story, if you want to use that word honestly, rather than as clickbait filler. Not that China invented a magical new material overnight, but that a country widely assumed to be constrained and boxed in by chip manufacturing restrictions has identified and is aggressively pursuing an entirely different and genuinely critical lever in the same race one that plays directly to an industrial strength, mass-scale precision glass manufacturing that the rest of the world hadn't fully appreciated as a semiconductor choke point until very recently. Whether China ends up leading this specific transition, matching the pace of Western and South Korean competitors, or falling behind as the harder reliability and qualification hurdles play out over the next few years, remains genuinely uncertain. And anyone telling you they know for certain how this race ends is overselling their confidence. But the fact that glass, of all things, has become one of the most closely watched battlegrounds in the global AI hardware race is not hype. It's a real, well-documented shift happening right now across boardrooms, factory floors, and research labs on 3 different continents. And it's a genuinely fascinating reminder that the future of computing hardware is being shaped as much by unglamorous material science as it is by the flashier, more headline-friendly world of transistors and algorithms. There's one more angle worth including before we close, because it says something about how quickly this shift is being priced into the wider economy, not just discussed by engineers. In mid-June of 2026, stocks tied to glass substrate manufacturing across Chinese markets surged dramatically in a single trading session, with several companies along the supply chain, from raw glass cloth producers to laser drilling equipment makers, hitting daily trading limits or posting sharp double-digit gains. That kind of rapid, broad-based market reaction is a signal in its own right. Financial markets don't typically move that fast and that widely on a story that's purely speculative hype. They move that way when investors believe a structural shift in an industry's supply chain is genuinely underway, and when enough independent companies, spanning materials, equipment, and assembly, all report tangible progress in the same direction at roughly the same time. Corning, the American glass giant with its own long history in specialty materials, signed a memorandum of understanding with China's BOE in May of 2026 to collaborate on glass core packaging substrates, among other advanced glass applications, a partnership that underscores just how seriously even established Western materials companies are taking this Chinese-led production surge, rather than dismissing it as a domestic curiosity. Put all of that together, the physics of thermal expansion and warpage, the display industry's unexpected pivot into semiconductor materials, the aggressive government-backed push toward packaging as an end run around lithography restrictions, and the market's own fast-moving vote of confidence, and you get a story that fully earns the attention it's receiving, even if the loudest headlines dress it up in more dramatic language than a careful engineer would ever choose. This is not silicon becoming obsolete. It's the unglamorous foundation beneath silicon finally getting the recognition, the investment, and the breakneck pace of innovation that the rest of the chip industry has been pouring into transistors for decades. And China, drawing on an industrial strength nobody expected to matter this much, has planted itself firmly and unmistakably at the center of that race. Let's take a closer look at the actual manufacturing challenge involved, because it explains why this transition has taken years to reach even this early commercial stage, and why glass, despite its obvious advantages, isn't something any factory can simply swap in overnight. Organic substrates, whatever their thermal limitations, have one enormous advantage born from decades of refinement. The entire global supply chain, every piece of equipment, every quality control process, every technician's hard-won intuition was built around handling a material that bends, flexes, and tolerates a certain amount of mechanical abuse without shattering. Glass does not forgive that kind of treatment. It's stiffer, more brittle, and dramatically more prone to catastrophic cracking if it's handled, drilled, or thermally cycled even slightly outside of carefully controlled parameters. Every single step of the existing chip packaging assembly line, built and refined over decades around organic materials, effectively has to be re-engineered, retooled, and requalified for a fundamentally different physical substance. That's not a minor software update. It's closer to an automobile manufacturer discovering that steel body panels need to be entirely replaced with a specialized ceramic, and realizing that every stamping machine, every welding robot, every quality inspection station on the assembly line has to be redesigned around the new material's completely different mechanical behavior. This is precisely why the through glass via drilling process has become such a closely watched technical benchmark across the entire industry, Chinese and Western companies alike. Drilling those microscopic holes through a brittle material without introducing invisible microcracks, cracks too small to detect during initial manufacturing, but large enough to cause catastrophic failure months or years later. Once a chip package is deployed in a data center running around the clock, is one of the hardest quality control problems in the entire field of advanced packaging. It's also why companies across the supply chain have needed to develop entirely new categories of specialized equipment, precision laser drilling systems capable of the exacting tolerances glass demands, alongside new inspection technologies capable of detecting defects invisible to older quality control methods designed for organic materials. Chinese equipment makers, companies like Hans Laser, have been investing heavily and rapidly in exactly this kind of specialized laser drilling hardware. precisely because it's one of the genuine choke points standing between a laboratory demonstration of glass substrate technology and a factory capable of reliably churning out millions of defect-free units at commercial scale. Traditionally, this optical technology sat somewhat separate from the main processor package, connected via external optical modules. Co-packaged optics changes that by integrating the optical components directly alongside the compute chip, inside the same package, dramatically shortening the distance electrical signals need to travel before being converted into light, which in turn reduces both energy consumption and signal degradation. Glass substrates turn out to be an unusually good foundation for this kind of integration, partly because glass's optical transparency and its precise flat manufacturing tolerances make it considerably easier to align delicate optical waveguides and photonic components than the more variable, less dimensionally stable organic materials allow. This is precisely why JCET's move into glass core substrates for co-packaged optics and high-speed optical modules carries outsized significance. It's not just a packaging materials story, it's a bet that glass will become the foundation, not just for keeping AI chips cool and well-connected electrically, but for the entire next generation of ultra-high-speed optical data movement inside AI data centers, an area widely considered one of the most important frontiers in data center hardware design over the next several years. It's worth returning, too, to the question of just how real China's technical progress actually is versus how much of it is still aspirational marketing dressed up as achieved fact, because that distinction matters enormously for anyone trying to separate substance from noise in this space. Independent industry analysts tracking the sector, drawing on supply chain reporting rather than company press releases alone, have generally confirmed that Chinese firms are narrowing rather than closing outright the technical gap with established South Korean and Japanese leaders in core processes like through glass via manufacturing and precision etching. Production capacity figures reported for companies like BOE, currently running pilot lines processing several hundred glass wafers per month with plans to scale toward roughly 1,000 per month by the end of 2026, are real and verifiable, but they remain modest compared to the volumes a fully mature, globally competitive semiconductor supply chain would eventually require. That's an important nuance largely absent from the more sensationalized coverage. China has unmistakably made rapid, well-documented progress and has assembled genuine structural advantages, but it has not yet definitively won this race. And the honest, sober industry consensus is that the next 2 to 3 years, as multiple competitors simultaneously push from pilot scale toward true mass production, will determine which countries and companies end up controlling the largest share of this rapidly growing market. There's also an instructive historical parallel worth drawing here, one that helps explain why industry veterans are taking this development so seriously rather than dismissing it as just another cycle of overhyped tech industry news. 2 decades ago, China's semiconductor ambitions were routinely dismissed by many Western analysts as perpetually several technology generations behind, constrained by a lack of foundational expertise as much as by equipment restrictions. That assessment has proven only partially true over time. In areas requiring the absolute cutting edge of lithography, the most advanced transistor manufacturing remains genuinely difficult for China to access, largely due to continued equipment export restrictions. But in adjacent related fields, ones that draw on manufacturing scale, materials science, and industrial coordination rather than a single scarce piece of imported equipment, China has repeatedly demonstrated an ability to move from follower to serious competitor faster than many expected, precisely by identifying and redirecting an existing domestic industrial strength toward a new, more strategically valuable application. Display glass manufacturing becoming semiconductor substrate manufacturing fits that exact pattern, and it's one many industry watchers half expected even before this year's headlines, precisely because it echoes similar pivots China has pulled off before in industries ranging from solar panels to electric vehicle batteries, where an initial, unglamorous manufacturing strength in one sector became the launching pad for global leadership in a related, higher value one. None of this guarantees the same outcome will repeat itself in glass substrates specifically. Semiconductor packaging carries reliability standards considerably stricter than solar panels or EV batteries ever did, since a single defective substrate inside a data center processor can mean a multi-million-dollar hardware failure, not just a slightly underperforming solar panel. That harsher reliability bar is precisely why serious industry observers remain cautious about declaring any definitive winner this early in the race, and it's why the most credible reporting on this story consistently frames China's progress as significant and worth watching closely, rather than as a settled, finished victory. But the underlying pattern, industrial strength discovered in an adjacent sector, redirected with striking speed and enormous capital toward a new strategic bottleneck, is real, well documented, and exactly the kind of development that reshapes how competitive an entire global industry looks within just a few years, whether or not any single headline captures that nuance accurately. So when you strip away the exclamation points and the shook the tech world framing, what's actually happening is this. The global chip industry has identified glass as the necessary next foundation for building AI hardware powerful enough to keep pace with the industry's own runaway ambitions. Every major chip maker on the planet, American, Taiwanese, South Korean, and Chinese alike, is racing to master it. And China, drawing on decades of unrelated but deeply relevant display manufacturing expertise, has emerged as a faster, better positioned competitor in that race than almost anyone outside the industry expected just a year or two ago. That's not silicon becoming obsolete. That's the ground underneath silicon becoming, for the first time in the history of computing, one of the most fiercely contested and closely watched pieces of real estate in the entire technology industry.